I'm going to talk about the language Ballerina, introduce Ballerina, and then also talk a little bit about why it's interesting for Java developers. Right? But this is not, I'm not going to bash Java, even though the title suggests that I'm going to do that. I'm a big fan of Java. I've been doing Java since most of you guys weren't born before that, I think. But there is a role that Ballerina addresses that Java doesn't address, and that is something that I want to get across, hopefully. Right? So I actually have, this is a full presentation that I usually take more than an hour to go through. What I'm going to do is just skim through this, and then I'm going to use an example of the system that we're building, one of the components for the elections platform that we're building that's written in Ballerina, and use that to explain and show some code that might be more interesting, I think, than just going through slides. Okay? If you have any questions, feel free to ask anytime. I have no problem. Okay, so I'm going to give a little bit of motivation why we're doing it, how is it different, and some stuff about what it's good for, and so forth. All right. Okay, so let me start with this. Why do you need another language? So there are plenty of programming languages. There are literally 100,000 plus programming languages, and there's new ones that have come out like Rust and Go and Swift and so forth. There are modern ones that have come out. So why do we need another language? So there are three different aspects of why we wanted to build Ballerina. By the way, Ballerina is a project that was started in WSO2 in 2016. So it's now more than 3 years old. We've had about 50 engineers working on Ballerina right throughout. So it's a fairly large effort for quite a while. So the first part is a business motivation. I think everyone understands the way things are moving now. Every business that operates anything has to have a digital aspect. That's his digital transformation aspect. And what that means is every functionality is coming off the network, and more people are depending on outsourced services. So for example, if you use Uber or something, Uber doesn't have the maps. They used to use Google Maps, they switched to OpenStreetMaps. They don't have a payment system. They don't have a delivery platform. They use Android, right? So they're just an aggregator of services, basically. It's an app that aggregates a bunch of services. This is the way everything works now. So what that means is, if you are a digital business, it means disaggregation is the norm. You're always taking up things and breaking it up into pieces, and then writing services that compose them together and aggregates them is also the norm. And offering that as a service to somebody else is how you become part of the value chain of digital businesses. So it's no longer produce something and put it out. It's now put an API and make other people consume it, and hopefully make some money off of it. On the side of computing itself, we've gone from a world where you actually had a computer, a physical computer that you ran, to having a virtual machine that started actually in the 50s and 60s, but became commodity and consumer in the 90s and the 2000s, to having containers, to now also going all the way to serverless and functions, where you don't really think about a computer at all. You just have some code that you want to run, and everything else is not your problem. Somebody else takes care of it. That's on the hardware kind of side, where how you run something side. On the side of architecture, we've had this concept called SOA for a while, and then we went to microservices, and now we have functions as a service, sort of even a smaller granularity piece of code that you run. And everything is about making things smaller so you can have smaller pieces that you can independently control and execute, right? So there's a minimalization. What that means is when you have a lot of small pieces, you also need to put them together to make something out of it. A small piece doesn't do anything useful. So if you see if you've seen Netflix is very famous for their microservices architecture. If you've seen their pictures about how the microservices integrate, they have a massive interaction diagram, right? And it's very complicated and lots of interactions. So you have to put them together. And earlier, the technology for integrating stuff was using some kind of middleware as a server, running separately as a server. But you can't run something as a server anymore because you're running them in a much more decentralized, distributed way. Then if you're using Kubernetes, the deployment model is using something called a sidecar, which is another process you run next to your process, and you group them together. But even that's becoming more expensive, and what Ballerina and so forth is trying to do is to say, we don't even need that, we just have some code, and the code takes care of fitting into the infrastructure. Right? So really, the concept of middleware as a separate thing is dead now, but middleware in return has gone to everywhere. The infrastructure you need is now part of the language. In fact, Node uses this term middleware to mean exactly that. If you use Node has this concept of middleware, which basically is a routing infrastructure, right? And that's something you just compile into the program you write. You don't actually have something else running for you independently. That's kind of the direction that we are seeing. So what all of this does is, there are many languages that do various things, but there's a set of aspects that are not well matched in the existing languages. So if you look at the spectrum of languages, there's a whole hierarchy of languages that are good for different things. There's no one language that is perfect for everything, right? C is now, it was in the late 60s, early 70s, C was invented. C is still the only language with which you would write an operating system. You wouldn't write it in something else, right? So there's assembly, there's Rust and C. Actually, Rust is kind of C level, but not quite because of its memory safety. It's a lot more expensive. So you still wouldn't write an operating system in Rust. C++, there's Go and Java and C#. Java and C# are basically the same. Go is a little bit not quite the same as Java because it doesn't have a separate runtime, but it also has a lot of the same managed aspects to it. So it's kind of straddles below Java and above Java in some levels because of its typing. Ballerina is kind of below that in the spectrum. Ballerina is a strongly typed language. It's structurally typed language. Is going to run natively. It doesn't run natively right now. We compile into a Java bytecode, but that's an implementation detail. And TypeScript Ballerina is actually closer to TypeScript than anything else in terms of functionality. But Ballerina comes with some other abstractions that is inherent in the language, which I'm going to talk about. And then you have like Python, JavaScript, which are much more scripting languages. And then you can go all the way to things like Bourne Shell and Awk and PowerShell and so forth, which are much more sort of glue languages, just for wiring a few things together, mostly with text streams in between. Right? So when we started the Ballerina, there's a set of design goals that we had. These have evolved over time as well as we learned more about what the language needs to do. Roughly what we are trying to do is to make network application development easier. So that when you write a program that is an application that is meant to run as part of the network, it runs resiliently, it runs reliably, it runs safely, it runs performantly without having to become an expert in every part of that stack, right? Which is the way you have to do it in most environments right now. So one key thing is providing abstractions for networking. And I'll get into this a little bit more in detail. We also use the concept of a sequence diagram as part of the programming model, basically. It's the way you program and the way you think about a program in a concurrency model, and from a networking point of view, is the sequence diagram. I'll explain some of this as well. And we want to make it the complexity that somebody has to learn in order to get started with this language. We want to try to bring it down as much as possible. The reason for that is most enterprise development scenarios, people write a piece of code and they go away from it and gets maintained for another 10 years or longer. And different people come and maintain this. So one piece of code is typically written once and read 100 times and modified 100 times. So the ability to understand what this program is trying to do quickly is very, very important. So minimizing cognitive load means trying to make it less complicated for the person to understand what is this program trying to do. We also want to maintain familiarity as much as possible. So if you're familiar with the language like C and Java and so forth, we want to keep that familiarity, so not make it unnecessarily complicated as much as possible, and so forth. So actually, let me just mention the last couple of points briefly. When you design a language, a programming language is a syntax, is a compiler, and so forth. But a software engineering is a lot more than a programming language. There's an entire life cycle of software engineering, from coming up with an idea to implementing the idea to testing it, verifying it, and performance evaluating it, and managing the life cycle and so forth. So Ballerina is designed to cover that whole space. So we have thought through what does it take to write a program for real, take it through environments, have versioning, have dependencies, have modularity, have sharing, have testing, have documentation. All of that is part of the product package that we're building, right? That's why it's taking a lot of effort to build this thing. So it's not just a language, actually, it's a complete platform we're trying to build. Let me just show you a simple, dumb example. This is a Hello World program, except it's a concurrent Hello World program. It has 3 parallel Hello World things that will happen when this program runs. I'll explain some more details later. So, and the picture at the bottom, you probably can't see it from there, but what it's showing you is a sequence diagram representation of the same program. Right? So it is not a picture that is drawn, it is the actual syntax tree of the code drawn differently, instead of in text, drawn as a picture. And I'll show you when we look at the code how that works. Right? This is a simple example of a service, writing a service. So there is a service is a first-class concept in the language. A listener is a first-class concept. I'll get into this and show you the real example code. So this one is just some random service that does something. And to get a service up and running is very simple. You say, I want to run a service on this port, and that's it. Everything else works for you. Consuming service is also equally easy, but we also again recognize that network interactions are different. So there's a syntactic difference in the way you write network interactions, and also there's an abstraction change. Right? There's a ton of examples. If you go to ballerina.io, there's a whole bunch of examples. You can look at them and look at various aspects of it. Right? Okay, let me talk a little bit about how Ballerina is different, and then we'll look at some code. So there are 6 different things that we put up on the website as how Ballerina is different, right? And what makes it interesting compared to other languages. So let me take each one one by one. So this one, programming the network. So the networking abstractions that we use in programming languages all originated from this thing called BSD sockets. BSD stands for Berkeley Software Distribution, which was a 1980s operating system project by University of California, Berkeley, which rebuilt a Unix implementation, basically. And they are the ones who invented this abstraction called sockets that everybody uses now, BSD sockets. Right? And every programming, and what a socket does is essentially says, okay, network thing is a combination of, in the case of a TCP socket, an IP and a port. And from the programming language point of view, it is just a stream of bytes. Right? It becomes an I/O channel, and you can read and write bytes to it. And the language doesn't understand that there is anything different about the network interaction versus reading a file, right? Or reading from another process or anything like that. There's no difference in those two things. And basically, all programming languages have just taken that and run with it. So Ballerina kind of changes that model and takes a slightly different model. And what we try to do is to kind of bring the abstraction of a network interaction into the way you write the code, right? So you don't think of a network connection as a file stream, a byte stream. You think of it as something different. So the abstraction has these components in it. There's a listener, a service, a client, and a client object concept, right? So listener is basically a way of saying, I want to open a port of some kind, whatever protocol it is, and I'm opening a door to the internet, right, to the network. And the door can be a door that somebody has to push in, or maybe a door that I have to go and pull information out, whatever, depends on the protocol. Right? I can give some examples later. When messages come through that, it gets dispatched to a service. A service is something you register with a listener, saying, I'm interested in these kind of things. Right? So it's like a routing engine, basically. Right? So it's like Node's routing engine is essentially what that is from a HTTP point of view. But it's more than HTTP, of course, for any protocol. When a request comes through a service, it gets dispatched to a resource method. A resource method is something that understands I am being invoked over the network, so I can't just return my value and say that goes back. If I want to send something back, I have to explicitly send something back. Right? So for example, if you're doing HTTP2 has these things about push, this promise concept, right? You can push a bunch of promises and then send it later. So all of that can be implemented very naturally in Ballerina, the way the model works. That's on the service side. That is on the incoming side. On the outgoing side, I know this is a bit abstract. I'm going to show you some code and give you some concrete examples, right? On the outgoing side, there's a concept of a client object. A client object is something that understands that there are network interactions, and they are called remote functions, the ones that let me interact with the network. And then remote functions are understood in the language as being network interactions. So the compiler can check the typing, compiler can check the safety, and so forth as you write the code. Right? You don't have to, you get a lot more safety right from the compiler. And then if you have asynchronous interaction, you can register a callback service that gets called as well. Right? So services and clients are typed. What that means is if you think about a protocol, a network interactions are not just a connection on the network, not just a TCP IP port, an IP address and a port, and a byte stream, but also there's some interaction pattern that is defined on top of that, right? So the type system for Ballerina is designed to represent that information as part of the language. So when you write a service, you can say, this is the kind of interactions I'm expecting to have. When I'm writing a client, I have a signature again saying, these are the input messages and these are the output messages that I'm consuming. Something outside. Once you have this written down, what it does is it makes the programmer aware what kind of interactions you can have with the remote endpoint, and the compiler can validate that. So the goal is to allow the compiler to completely be able to guarantee that if you're doing a network interaction with the other side, it is type safe. Right? There's a concept called session typing. We only have a lightweight version of it here. This is a fairly new concept in programming languages, which is a way of typing concurrent interactions between two parties. Right? It's called session types. So we have a very lightweight version of session types built into the language, and we are going to be adding a little bit more as we go along. So then you'll have a complete sort of a signature for a network service. And when you write a client that uses that network service, the compiler itself can guarantee that if it compiles, your network service interaction is correct with regards to what the other side is expecting you to do. Right? So the goal here is to reduce the likelihood of writing a network application that doesn't work at runtime. Right? So it doesn't, just to be very clear, Ballerina doesn't do anything that you cannot do with Node or Python or Java or C or whatever. Everything is about making the programmer productivity better so that when you write the program, if you get it past the compiler, it's going to work. Right? That is the goal. Right? On outbound calls, network is very finicky. Things go wrong all the time. You try to do a DNS lookup. It doesn't work right now, but do it again, it works. Right? These kind of things happen all the time. So there's a level of resiliency that you need to build in. And if you don't do that, often programs become fragile. That's why you do something on a browser, it doesn't work, you refresh, it works. Right? And if you have a human being on one end of it, that's okay. But if you have a program on one end of it, it makes the entire system fragile. So people have to program all this resiliency stuff. If you're in Java, you use Hystrix or something like that, right? If you want to do some of this stuff. This is all built into the way we've designed the language and the libraries around it. So you don't have to do that. It's sort of automatically retry, failover, load balancing, all of those are kind of part of the framework itself. So another important point is everything is non-blocking and asynchronous. That is, you write Ballerina applications as if everything is blocking, but at the underlying thread level and the OS resource level, absolutely nothing gets blocked ever. The entire I/O is non-blocking underneath. So at the application level, you don't have to have a callback hell to write code. You don't have to say when something comes, call this function, which has another callback inside, and trying to debug something where there's like 3 levels of callbacks is very difficult. In Ballerina, you just do a blocking call, and what you're really doing is a callback, but at the programming level, you don't worry about that. You simply do it as a blocking call. The resource management is done by the runtime libraries, and you just program it as if everything was completely synchronous, right? Completely blocking. And it's not blocking at all, but it works conceptually in the same way. Services, of course, concurrent. I won't get into too much of this. There's also network security. So one of the other key aspects about network services is when you write a network program is you have to worry about security. You can't think about security afterwards as to how you're going to secure the service or what you're going to worry about the data. So there's a concept called taint checking. Actually, Perl has had taint checking for a long time, which is a way of saying some data I get over from somewhere is not clean, and I must clean it before I can access it. That's what tainted means. So Ballerina's model is if you get something over the network, we assume it is tainted. And if you are writing something that is sensitive with regards to taintedness, for example, a database client which doesn't want dirty data coming in, then you have to explicitly clean that data before you can pass it in, right? So there's a way to say, I have cleaned it. Now, obviously, the compiler cannot guarantee that you have done whatever you need to do to clean the data because it depends on the data you're trying to clean. So for example, if I'm trying to clean for SQL inserts, I have a different kind of escape versus I'm trying to do it for URI escaping and so forth, right? So those things have to be done based on the programmer's needs, and we are providing a collection of libraries that you can use. But overall, the model is if you have a piece of code that is sensitive to the quality of the data, it can mark that data as tainted, as sensitive, and then the compiler will guarantee that it won't allow a tainted piece of data to be passed in. So when you compile a function, we keep the taint signature along with the function. So if you link it somewhere else in another module, somewhere else even, we know, and the compiler will not let you compile it. Right? And there's some additional work we're doing around Let's Encrypt and so forth. One of the things about network applications is things do go wrong all the time. So error handling is very important, and having a proper error handling strategy. This is another area where programming languages have evolved quite a bit and been very different. So if you programmed in C, the way you handle errors in C is typically most system calls return -1 as a way of indicating something went wrong. And the idea there is you're using a value that is outside of the normal range of return values, and the caller is supposed to check that value, and if that value is present, that means something went wrong. C++ introduced exceptions. Java enforced exceptions, basically. Java's model is something goes wrong, you send an exception. And Java has checked exceptions versus runtime exceptions to deal with the fact that sometimes it's just too damn annoying to catch everything. But whenever something goes wrong, it's returning exceptions. Exceptions are convenient to program, but they're also a very expensive way of handling errors. Because in many cases, errors are normal, especially in network interactions, errors are normal. They're not abnormal. So you have to write the program to be able to handle those errors. Right? You can't say, well, something went wrong, I give up. Because something going wrong is part of the normal behavior of network interactions. You're on your Google app, suddenly you can't get to the map. It can't say, well, sorry, on your Uber app, you're trying to get to the map. If the network doesn't get to the map, the app cannot die. Right? It has to gracefully recover. That means somebody has to program that thing. So handling those explicitly with exceptions is actually a very inefficient way of handling it. Go came up with a different model. Go introduced his concept of, Go has his concept of multiple return values from a function, and the n+1, the last argument is always the error value. And if that value is there, you're supposed to check that, and if that value is present, it's got a value, then the other return values are invalid, and you're not supposed to use it. That's why in Go, there's a joke with Go that every time you call a function, the next line is, if error not equal to nil, return that error, right? The problem is it relies on the programmer to do that thing. If the programmer ignores the error and continues to use the other value, there is a value. So Ballerina's model is a bit different. Ballerina has something called union types. Union types means you can say the value of something is either this or that. And it's a union of those two things from a type system perspective. It's a union of those two things. I'll talk briefly about the type system later. And so the caller who's getting the return value from this function knows that I can either get a string or I can get an error. I can't get both. And if I'm getting something which is string or error, the variable must be declared to be of type string or error. And I have to handle that. And so I'm forcing the programmer to handle that. Now there are some convenient things for saying, okay, if it's an error, return that upward and get on with it life. So there's some conveniences like that to make it more tolerable. But by doing this, you are forcing the programmer to handle errors that are supposed to be handled. Right? You can't ever skip it. The compiler won't let you skip it. There's also something called panic. Panic is like an exception, basically, like a runtime exception that you can throw. And then you can trap the panic and convert it into an error and handle that separately as well. But panics are mostly for unhandleable errors. If you run out of memory, there's really nothing you can do because you ran out of memory, right? Things like that, or divide by zero, these are things that are errors that are not occurring as part of the normal execution, but things that happen because the program is screwed up. Right? And the program is screwed up now. If you're writing an end-user application, you still have to handle that. You have to trap that panic and catch it and do something with it. But otherwise, these are like, okay, there's a fundamental bug, so there's no point in trying to recover because you can't recover from it. Right? So I mentioned sequence diagrams as an important aspect of Ballerina. So when we, in WSO2 in the last 15 years, whenever we had a complicated customer problem where there was some complicated scenario where something went wrong, we found that every single time we explained to them in a root cause analysis document or whatever mechanism, that you would draw a sequence diagram to explain what went wrong. Right? Because sequence diagram is a great way of capturing concurrent behavior and explaining, saying this person sent this one sent this, and here there was a race condition, that is why something went wrong. And then you can convince them, saying, okay, that won't happen again because we've done this to prevent that from happening. Right? But sequence diagrams are not being used to program applications. They're used to describe how a program works. So Ballerina changes that. And the model in Ballerina is that you actually write the code as a sequence diagram. Now, a concurrent code or network code. If you're not writing concurrent code, there's no sequence diagram nature. It's a single actor. So you write the code one normal way. But if you have multiple things, you always think of it as the same way. And the code, the syntax of the language is designed to make it possible to always represent the entire program as a sequence diagram, right? And we can actually trace down the sequence diagram through the entire length of the program. I'll show you some of that in a little bit. Right? And we treat network interactions as concurrent actors in sequence diagram, in the diagram. Because a network endpoint is actually a concurrent actor, right? I'm not in control of it. It just happens to be something that's running, and my only interaction is by sending messages back and forth. And that's where the typing comes in to decide what can I send and what can I not send. Right? And there's a feature coming in our VS Code plugin where you can actually, and the IDEA plugin, where you can put a breakpoint in the sequence diagram itself and debug it, saying when it gets to this point, I want to stop and look at the code, right, and see what's going on. Right? The concurrency model also ties to sequence diagram, because if you think about concurrent programming, if you look at Java, for example, Java has threads. Go has something called Go routines, and many other languages have various forms of thread packages built in. The problem is that in every one of these languages, concurrency is a second-class concept. Right? That is, to make something concurrent, you have to teach something a lot more complicated. In Ballerina, the model is everything is always concurrent. You can do concurrent things without any overhead, any sort of intellectual overhead, because you can think of it as a sequence diagram. If I want to do two things, I draw two lines. Right? If I want to explain to someone saying, okay, when something happens, now do things in parallel, I draw two lines and say, do something here, do something here. And the syntax of the language captures that exactly. Right? These are called workers in Ballerina terminology. Each line is a worker, so you have two workers. And you just write the workers, and one worker can talk to another worker, and so forth. And the compiler also makes sure that if one worker is sending messages to another worker, and the other one sending messages, that there can't be any deadlock. That's also part of the session typing. We look at the signature of the interaction between every two pair of workers and guarantee that it cannot have a deadlock. Right? And again, we have a lot of limitations right now in the session typing, so we don't allow certain kinds of interaction. For example, in a loop, you can't be sending right now. That's going to change. We're working on something called generators, and then it'll allow a lot more flexibility. The underlying execution model is something called strands. Strands are sort of like lightweight threads. Java has something coming up, fibers, Java fibers, I think Java 14 or something going to have that, which is a similar concept, which is basically essentially a call stack that you can bring up, and you can call stuff within that. And workers are the units of execution that you stack them up, right? And a strand is represented by a future because it's a call stack, and then you can always get back whatever the last thing in the call stack finishes, you can get back as a value of the strand, right? So the way you write concurrent code in Ballerina is just very straightforward. So every function has a default worker that is running in the caller's context. I'll explain this when you look at the code. And if you want to write something in parallel, you just say, I have another worker. And so that is just a syntactic way of writing down the sequence diagram. Right? And one inspiration for this was if you use something called websequencediagrams.com, which is a fantastic tool actually for if you want to draw a sequence diagram, you just write down saying this goes from here to here, this goes from here to here. That's one of the inspirations that for how we designed this part of it. Right? All right. Let me talk a little bit about the type system. I'm going to try to finish off quickly so I can go look at some code. So Ballerina is not an object-oriented language. It's very strictly designed not to be an object-oriented language. It does have objects. You can do objects. You can live only with objects if you want. And we find that a lot of Java programmers, when they come to Ballerina, naturally write everything in objects because that's what you're used to. But it also has functions. It has functions as values. You can just, and it has types, records, which are not objects. So data structures can be just defined as records, which if you're familiar with C, it's like structs, basically, right? So you don't have to do objects. Why not? Why is it not object-oriented? Because object orientation and distributed computing don't work well together. Objects are data plus code. Distributed computing is data only. There's no code. Java tried to do this. Lots of systems tried to do this. Corba tried to do this by sending code back and forth or sending serialized versions of those things back and forth. But it really doesn't work. It causes significant coupling across systems, and no one ever really does RMI at scale and so forth, right? If you look at the internet, nobody ever sends objects back and forth. You send some data back and forth. So Ballerina's type system works very tightly defined in a way that data becomes a first-class concept. And the way we describe data is also allows a type description to work as a schema as well. So schema describes how a particular piece of value is written down, and a type describes how a set of values are structured. But the way we've designed it, they work back and forth. And what that does is when you want to data bind from a particular value, it becomes just a typecast. You don't have to do anything else. I'll show you some examples. The type system itself has sort of all the usual stuff. It has normal simple values like Boolean and int and float and so forth. It has decimal as well, and we'll be adding another type called timestamp into, I think, into the next release. There's also a collection of structured types, and really, but just two kinds of structured types. That's all we have in the language. And that's also by design. They're basically ordered lists and mappings. Ordered lists are arrays and tuples. And arrays are things where you have the same type of value repeatedly occurring, right? An array of integer, array of person, array of whatever. A tuple is something where you have different kinds of values coming together, right? A pair of two things, a person and an address, for example, would be a tuple. And mappings are also similar concept. A map itself, a map is like an array. It's the same kind of value that you have in the map, and a record is a mapping where there's named fields with different kinds of values, right? And what this actually turns out to be an exact match for JSON as well. So if you have any value in JSON, Ballerina values and JSON values are completely in sync. So if you have something in JSON, you can just bring it into Ballerina and just use it like Ballerina types. Another aspect of Ballerina is about writing a program and getting it to run in a cloud environment. So in today's world, when I first started programming is in the late 80s, or mid 80s actually, actually even before mid 80s, we would write a program and you were in a computer and you had the complete computer for yourself. You write a program, you compile it, run it on that computer, right? Today, nobody has a physical computer for anything except your laptop. Right, for real purposes, right? So you write a program, you compile it, then you build it basically, you package up everything together, then you make a Docker image out of it, then you write some YAML and get it out into a container environment, some kind like Kubernetes or something, and then you run it and you can observe it and so forth. So if you look at that process, it's no longer the programmer who's in control of how something runs. There's many other steps that somebody has to do. And the problem with that is it again decouples the level of control that the programmer can manage across these things, and makes it much more complicated for the programmer because you have to learn all these different things. So what we've done is we brought those into the language through annotations. So the compiler gets involved in the compilation process. So for example, if you put these annotations, that Docker annotations I put in, if you build this thing, you get a Docker image coming out of it, right? So the compiler runs the Docker build on this thing and builds an image for you. Because you said I want a Docker image, and you can put there are other options. You can say where the repository is, what the credentials are, all that kind of stuff, right? And you can take it one step further and you can describe a complete Kubernetes deployment. So if you run this thing, it'll generate the YAML files for the Kubernetes deployment and it'll tell you what kubectl command to run, right? So you don't really have to understand and play with the YAML at that level of detail. You can think at a higher level abstraction saying, what I have are Kubernetes services, I have a Kubernetes deployment, I have an ingress, and I write those things and it just jumps right in. And it's also pluggable. It's not meant only for Kubernetes. It's essentially a compiler extension. So the design point there is we recognize that during the build process, you have to do more than just compile the code that you wrote. You have to fit into the environment. So there's an architecture for how you plug in something to the compilation process so you can run arbitrary code. And that code can rewrite the program, can rewrite the syntax tree, can generate multiple binaries, can generate YAML files, whatever you want. Right? That's how that works. So I think we've done plugins for some Amazon stuff. There's a function, there's a Lambda plugin, and like that. So you can plug anything in. Right? One of the other things about a language like this is, since we are dealing with network applications, there are lots of different network protocols, data formats, data stores that you have to deal with. So the design point is to be what's called a batteries included model, which is that we have pre-written all of that stuff for you. Right? So you don't need to go find somebody else's HTTP library and so on. Right? All of that is supposed to be pre-provided. So there's a whole bunch of stuff that's provided out of the box and more as we go along, basically. The goal is to say, if I'm going to write something in Ballerina, if it's some existing network protocol, somebody, it's either it's part of the platform or it's part of the sharing environment that you can pick up. The other part that I mentioned is about using Ballerina as from a developer point of view. Programming is not just a matter of writing some code and being done with it anymore. Right? It is an entire life cycle involved with writing code. It's about documentation, it's about testing, it's about modularity, it's about sharing, it's about publishing code, everything, right? Observability. So we've worked through this entire tool chain, and there's architecture for every one of these things. And the tool chain supports the whole life cycle, right? So there's version management, there's Ballerina Central, which is a module repository. So you can push a module there, somebody else can pick it up. There's documentation plugin. So if you're pushing something to Ballerina Central, documentation is required. And documentation is in the code in a variation of Markdown, basically. And you have to put it. We don't allow you to push something to the public repository for any public symbols without documenting it. Because the whole point is, if you're putting something out for somebody else to use, they should be able to use it. For them to use it, they need to have documentation. And the documentation plugin also checks to see whether you at least referred to all the parameters in the function or the object or whatever that you're documenting. Right? So a lot of stuff done to try to make it so that the developer does the right thing when they write the code the first time. Right? Sometimes this can be a little bit annoying. Like, I just want to get this damn thing out to my friend and I can't be bothered documenting it. Right? But that's an intentional decision to do that, because the point being that in most practical scenarios, code is written once and then many people live on that code for a long time. Code always lives longer than you think it's going to live. And as a result, taking that bit of extra effort at the beginning is worth the pain to make the code more usable. And that's why we force this thing on you. So what's it good for? Ballerina it's a full programming language. You can do anything with it. But obviously, it's not meant to be writing an operating system or anything like that, right? The use cases are more towards that end where you're doing network applications because of the way it fits into the structure. So BFF services, if you're writing backend for front-end services, Ballerina is a perfect fit because you need to publish a service, you need to consume a bunch of services. And the abstractions in Ballerina are absolutely perfect for that. Data services, you're talking to some data sources and publishing it as a service. That was one of the design points for it. There's some more work we had to do yet to finish it, but it's a very, very good fit. The Java side of it, because there are, I'm not talking really about the implementation, but the compiler, the plan is to have multiple implementations of the compiler. The one we have right now is called JBallerina, which implements Ballerina by generating Java bytecodes. And because it's generating Java bytecodes, we can interact with any JVM library. Right? So you can talk to any Java application, any library that you have directly. You can import it, and I'm going to show you in the next page simple example of that. If you're doing Kubernetes stuff, this is much easier. If you're doing gRPC stuff, Ballerina code is a lot easier simply because the asynchronous model versus the other ways of writing gRPC stuff. If you're doing integration, if you're using an ESB world is dead, this is the way you should write that kind of scenario, because it's much easier to write those things, and it's a proper language instead of being some weird DSL, basically. And so on. There's a bunch of scenarios where Ballerina is actually quite useful. So this is an example of how the Java interop works, Java integration works. Basically, you import the Java package, Java module, and there's a way of putting some annotation saying the implementation of this function is actually in Java. Right? And there's some details on that. You can see there's a document on that where you name the class and name the method. You can also invoke object methods, not just static methods. You can pass Java values back and forth. They come as an opaque handle into Ballerina, so you can't do anything with it in Ballerina. And for the types that do map, so for example, int and integer and so forth to Ballerina int, they map correctly, right? Because we both follow the same IEEE standards, so those map. And those that don't map show up as a handle. And then you must use supporting functions to get actual values. So string, for example, is a bit annoying because Ballerina strings are not UTF-16 that Java does, so it's a bit different for that. Okay, status of the language itself. So we just released 1.0 a couple of months ago in September. It's based on the language spec 2019 R3. The language is evolving yet. There's a lot more work. We have a long list of things we are doing. And we expect it to take several more years of work to get it sort of completely done with this list and any other stuff that will come along the way. Languages take a long time to establish. You might think Go is new, but Go is now 10 years old. You might think Rust is new. Rust is 13 years old. I don't know how old Swift is, but it's not 5 years. It's longer than that. Python is like 25 years old, and so forth, right? So these things take a long time to get to the top of the pie. So we expect to keep evolving it and adding more stuff. All right. So I'm going to switch to explaining the example code. So what Ballerina is trying to do is not an experiment. This is an industrial grade programming language project, and the goal is to be a language that sticks on for a long time. It addresses a set of problems that are very present in the way applications are being built today, but addresses them in a different way than most languages have done. We address them in a way that tries to bring the networking aspects and the security aspects and the concurrency aspects that we always have to deal with now into the programmer's thinking, instead of into frameworks and libraries and into sort of third-party functionality. Right? So, and the diagramming model and all of it is designed, and the type system, everything is designed to make that use case really, really simple. So you write a program, it just works out of the box and you don't have to worry about anything. Okay, any questions before I switch over? No? Yeah. Yeah, so we are compiling to Java bytecode, not to machine language, right? And the JIT stuff works below that, one level below. So we have basically there's a significant Java runtime library that gets involved. So we call that for a lot of stuff. So a lot of the types and so forth get compiled into different Java classes. And the basic values are built in already. We have a Java library that does that. So the compilation, the complexity comes around the concurrency model, because we basically need continuations to do that. So we generate a continuation model for function calls in order to implement the non-blocking I/O and the non-blocking programming model. Because when you write a Ballerina code, you just say, in the code itself, you just say call this function which is doing I/O, but the thread, we don't want that thread to block. So there's a continuation model generated. So we release at that point, and there's a continuation generated, so you can jump into that point when the code is ready to continue. So there's a bunch of, if you're interested in that, you'll have to look into the code a bit, and happy to help, but yeah. Okay, I'm going to talk a little bit about a project that I'm doing right now, and that's using Ballerina. So LSF, the Lanka Software Foundation, is a nonprofit thing I founded in 2003 along with a bunch of other people. This is an organization that originally was focused on helping Sri Lankan developers create open source technology and take it to the world. In 2018, we changed our mission. Now what we're doing is taking technology and helping the government improve how software is built in the government. We don't charge a penny from the government. We work with different parts of government. We get money from somewhere else, and we build. We provide architecture help, we write code, we do whatever it takes to build the right kind of software for the government. Because government buys software, actually big organizations buy software like they buy furniture. Right? You say, I have a room this size, I need 100 chairs. And software doesn't work like that, because software is evolving, and often the users of the software don't know what the software is going to do. So you can't wait for 2 years and get the thing and say, okay, now your problem is solved. Because no problem is ever solved in the world of software, right? Software is like getting married. You get in, you don't get out. You got to keep going, basically, and keep evolving it, right? So what we are doing is going with different parts of the government and helping build the right software architecture, and in some cases actually building the underlying tools, in some cases building the software itself. So education, for example, has a system now where all students are being entered. Every single student is going to a database by end of this year. They'll have a complete record of every student from now on. So if you move schools, the system will know. Actually, from next year, most probably, you won't be able to do O-level, A-level, or grade 5 exams unless you're in the system. So you won't have to rewrite your name again once you get into that. Right? So elections, about a year and a half ago, we started working with the Elections Commission to really build a software platform for running elections. Let me be very precise right up front. This is not for voting. The voting is on paper the same old way we're doing it, right? So it doesn't change the voting process. The voting process is set by the Constitution. If that is to change, Parliament has to make that change, and then we can implement electronic voting. Implementation is not the hard part. Getting it, the policy and the convincing people that, convincing people that it's working is the hard part. Anyway, I'll keep going while this. So the goal of Elections Commission's legal mandate is actually to be an election as a service organization. It's like examinations department runs examinations for about 80 different organizations. So their mission, in their scope of work is you can run an exam for anybody. You want to run a Java exam, they can run it for you. Same thing with elections. They can run election for anybody on anything. But they don't have the infrastructure for doing that. So what we're trying to do is to work with them to say, we'll build jointly with them the software platform to be an election as a service platform, with the public elections being one particular important use case of that. But then they'll be able to sell elections for anybody else. The Lawyers Association wants to do elections, they can contract these guys and pay money and get an election run, right? And they'll provide the transparency and accountability and so forth that they want. So this is a large project. There's a bunch of people involved. It's not we have a lot of volunteers. I think maybe about 75 to 100 people have volunteered now so far over the history of the project and written various bits of code. This is going live for this election, the first part of it. So this is going to be managing, the incident system's already live. So whenever somebody complains about incidents, there's a system into which everything goes in. There's a dashboard that they monitor. The daily report that comes out saying this many incidents happen comes from that system now. And so forth. The other components that will go live for these elections is a results tabulation system. So when they add up the votes in the counting center, when they add up the votes, that's first done by hand, and then they get aggregated at multiple levels before we see saying this many votes went to this person. That aggregation process is going to go into this software. But again, just to be very clear, there are two other parallel manual systems that are running for this election. Right? So it's not the software that's going to decide who wins. So there's no computer Gilmart possible, and I have nothing to do with computer Gilmart. This is a software that is running as a redundant system for two parallel manual protocols, right? One running at a district level, one running at a national level. And if all three results don't match up, they won't release the results. They'll sync up, make sure that whatever the problem is, find the problem, fix it, get all three to match up, and then release the results, right? So one part of it is when a result, so there's a tabulation system that produces, adds up everything, and the Elections Commission signs off. Then that system says, okay, we are ready to go. Now we want the result released to the public, right, to media. So that is the results dissemination problem. So that is once a result is committed at a polling division level or at a district level or national level, whatever, the committed means the numbers have been verified, the commission has manually signed it, all three commissioners are going to sign it this time, and the document has been scanned in and re-verified that the data and the document match. Then you press this button saying push it out. Push it out, it comes here, right? And so that is that step one. Then it comes there, and then we store it locally so that we can reprocess, and in case there's a crash and so forth. And then this is only for media, right? So the media has to pay to subscribe to this service. They charge tiny amount, like 75,000 rupees. These TV stations make millions out of this thing, so it's nothing they're charging. But they get basically first an SMS notification saying there's a result coming, because people are sleeping or whatever, and they have to get up and say, oh, something's coming. Actually, previously there was an FTP server. This time we are not having the FTP server. This is a slightly old diagram. Because earlier the model was they would push it to an FTP server, people would log in and check and pull it down, right? And people will be constantly logging in and checking, is there anything, is there anything, is there anything? So it was killing the damn server all the time. So now what we've done is we have a WebSub is a protocol, which is a webhook protocol. It's a standardized version of a webhook, basically. So we're using WebSub. So the organizations register a subscriber with this, and whenever there's an event, it gets called. So we deliver the result right into their computer, right? And then something happens there. And there's also a website that it generates automatically that you can go in and see how many results have been generated, whether I missed anything. There's a sequence number, so you can see whether I missed anything because my connection was down, it didn't get delivered. Obviously, there's retry and all kinds of stuff, but still, if something goes wrong, you can go and see all the results that have been released so far, right? From a scaling point of view, it's really not a big deal. The incoming result load is quite small. So the formula is we get 409 or 818 results coming out. I can explain that. So we have 160 polling divisions, right? So that's a unit of result that we get. We have 22 districts. So every district has a postal vote, which is like a polling division. So it's 160 plus 22. And then you have a 22 districts. So you get the polling division vote, you get the postal vote, and you get a district-wide result, which is the aggregation of all polling divisions and the postal vote for that district. And then while that's going along, there's an incremental current running total result always released to media. So which is like, okay, if I release 2 polling divisions, so after one, you get another one saying this is aggregate. After 2, you get another one saying this is a total of the 2. Right? I don't know why they do that, because those guys should be able to add up the numbers, but this is the way they've been doing it, so we're continuing that. So you can get up to 409 results for the entire election, basically, out of that. So it's not a lot, because it happens over a number of hours. And this time it's going to be many hours, because that sheet is 23 or 26 inches long. And they're actually issuing everybody a piece of wood to keep it flat when they open it. Because it's apparently, you have to fold it 8 ways to get into the box, and when you open it, it goes like back together again. So they're giving them a piece of wood to keep it flat, and they have to read it like this. Your head has to move because it's this long, the sheet. Right? So it's going to take time. This time the results won't come out. Next morning when you get up, I don't think there'll be much, if any, out. Maybe the postal ones will come out because they're small numbers. Right? So it's coming out over a period of hours. So the load is really nothing from the input side. On the subscription side, there are on the order of 100 to 200 media organizations that will subscribe. So not a whole lot, basically. And some of them will be polling the website. So relatively not much scale. So we're not worrying about running this. Everything is running in a Kubernetes cluster, the entire deployment. And we have multiple HA, multiple DR sites, a whole bunch of stuff set up. But this one, we are not worrying about scaling. And if something goes down, we can just restart it, and it'll come back up, and the data is saved anyway. So there are 3 pieces to this. There's a distributor, that's the one that gets the result and pushes it out to everybody. There's a subscriber. We're actually giving the media guys a program, because we're not expecting them to be able to write a webhook handler and do all that work. We're giving them a client, which is a webhook client, web sub client basically, that subscribes to the topic, and when something comes, a file appears on your machine. So all they need to do is just run that program, and files appear on their machine. They get an SMS and a file appears. And the file can be in JSON format or XML, so we locally convert it. We send the result in JSON, and you can pump it out as an XML, or we're going to generate an HTML as well, so you can have a local website if you want to see all the results that have come onto your machine by then, right? And then the third one is a test generator, because we need to be able to test this bloody thing. So what we've done is we're taking the results from previous election and pumping it in random order, and then generating the results in. Right? The subscriber side is straightforward. It's just a web sub client. And then it generates a file. That's it. This is roughly how it looks, the distributor side of it. So now I'm going to show you the code. So I'll just show this, and then there's a container that has 2 ports open. One that is receiving the results from the tabulation system, and one that is open to the public media with authentication. Right? I'll give you the URL. You can check it out now. But it's not authenticated right now. It's on a test system, and you can hit it, and then you'll see the results that have been produced. And when something comes in, what we do is we save it, and then we push it out. We generate the website information, and then it goes out through the hub to all the subscribers. Right? And there's an SMS that goes out as well. Right? So it's straightforward. And the test generator essentially, so there's a temporary thing we put in order to be able to publish results into this, in order to test it. Otherwise, it's going to be within the Kubernetes cluster. You can't get to it from outside at all. From within the cluster, it'll publish from one subsystem to another. For temporarily, we have exposed that so we can actually push something out. These are all running in dev environments and test environments right now, so not the production environment. And then the test generator simply lets you actually start a test on the website, because people need to be able to test their code. So you can go to the results test website right now, and if there's no test running, if your test is running, you'll see, because it's generating a result every 10 seconds is the way it's set up right now to produce a new result out. And then if it's done, you can press start another one, and it'll start another one, right? And just push into that randomly, and computes what it needs to compute and so forth. Okay, so let me just show you some code. I'll switch to showing you. Okay, so this is the Ballerina syntax for, remember that distributor guy had 2 ports being opened, one for results to be given to it, one for the public, the media companies to check what's going on, like log in and see what there is. So there are 2 listeners. Listener is the terminology we use for a port that we open and based with some protocol. In this case, it's an HTTP listener, and I've called it results listener. And what it is doing is it's saying, okay, get the port number from configuration. If not, pick up 8181, right? And then it'll just open up that port, and it doesn't do anything yet because I haven't attached anything to that listener. So if somebody connects to it, it'll accept the connection, but it's got no place to dispatch it to, so it'll just forget about it, right? And then the media listener is this is the result system, the one where results get pushed into it. The other one is where things come from the media side, right? And then if you look at the results listener, this is the code for that. So this service, it says this is a service on that listener, right? And that means I'm attaching a service to that listener, and there's a configuration here that tells you on what path I'm assigning it, right? So base path means this is the path of that HTTP server that I want to take over for this service. And then within that, I have different subpaths that I can take. So here I have a resource function. A resource function is the entry point that you're actually calling from outside. I don't know that you guys can read this, but so this says there's a resource function called receive data. It gets passed in a caller, which is a representation of the guy who's calling, so I can reply back. And the request information, and then the parameters that I put in here. I have a URI template here that tells the dispatcher how to break up the request and pass me the parameters, and they're typed. So if the type doesn't match when it's coming in, you'll get a bad request going back to the client. Right? The code doesn't have to deal with any of that stuff. The data binding into JSON is already done. Verification that so the body here I've said is JSON, and the type of that variable is JSON. So if it's not a JSON that somebody sends in, I won't get called. Right? There'll be a log entry going out saying there was a bad request, and I'll get a not 429, whatever the right HTTP error is, comes out saying it's not a good request. And then there's some stuff. I build the structure, and then call this thing, save the result, and then push it out. Right? Published result is a function that basically just pushes it out. Here we are still working on the SMS code. It's not done yet. So the SMS code will run in parallel with the other part. Right? And the web sub protocol, basically I take the result and go contact the hub and say push it out to all the subscribers. Right? Now I can show you what this program looks like. So if you're using the VS Code plugin, so let's just start at the top. This is a service here. So which is what is the service called? Receive results service. So if I click on this one, it'll show me all the resources that are in the service. Right? Now if I just want to go down to one of them as a sequence diagram, it's showing me the code. It's showing how the received data code. So if I expand it out here, it's saying what happens here is that this is completely from the code, right? I get a request coming in, and then I do some work, and then I call save result, and then there's a function called publish data. I call a function called publish data, and I've opened it, but I can collapse it. So if I open it, let me reopen that. So it shows me what the structure of that function is inside. And then on the website side, again, a website is just another service that is attached to slash. So, and when you hit this thing, it dynamically generates a web page and just delivers it out. There's no CSS or anything yet right now. It's just the basic template that shows you the results that have been accumulated so far, right? And there's also another path you can hit called all results, which gives you a JSON that has all the results that have been accumulated so far in one single JSON array, and just returns that. So this is showing you how to get a JSON array. I want it in reverse order, so I looped it backwards. So I took I have a cache of all the results in memory as well as it's in the disk, so I don't have to go back to the disk all the time. And I just take that one and I loop through that and append it into an array, a JSON array, and just say, okay, send the results back. Right? So if I look at this function, if I look at all results function somewhere here, right? It shows me the code for that, okay? And here, because this is a resource, the call comes in from the service from outside, right? And my code runs, it does whatever it does, and then it sends a result back. So it shows up, so it goes back to the guy who called me, right? So if there was more concurrent stuff, for example, I'd see more lines. If I was calling another service, I'll see that here. If I go to, actually, let me just show you how this looks like. So this is the public site right now. So there's am I connected? Yeah. So this is a generated site from that code. This is running on a test server. it's showing you, so right now it says 204. This is not sending incremental results, so 204 is the total, is 160 plus 22 plus 22. So let me just start another test. If I start another test here, so 36 times this has been started today. That's what the sequence number there says. If I reload this page, there won't be anything, there'll be one. So 37 run here, and there's only one result here. So after 10 seconds, there'll be another one, and I can look at the JSON value for that, and so forth. This is for the media guys, right? But this also gets pushed, so there's another one now, right? It gets pushed back to the various people. So all of that was done. So there's a few, basically, the convenience with Ballerina is when I want to write another, open another service and so forth, it's extremely straightforward and you just write it, and dealing with JSON is very simple. So if I show you the, this is the saving code from the distributor. So this is one that's dumping stuff into a database as well. So if you look at save result, it'll show you the database as well as a remote participant here, right? So as a function that gets called with some result, I do some update and do some more stuff and return. Right? All right, I think I've gone exactly 1 hour. Anything else I can show you guys? Any questions? So this is the test driver. This one basically shows you how as usual, demo syndrome, something, for some reason, doesn't want to draw the picture for me right now. Anyway. Okay, any questions? So this is an example of a tuple type being used. So this is, I'm looping over an array, list basically of the results, and I want both the key and the value. So I declare 2 variables of type string and JSON, and I give them 2 names, and I say for each one of those things, and then I iterate through that. Right? And this syntax here is saying generate me numbers from 0 to n-1, 0 to that number, etc. Any questions from anybody? All right, well, give it a try if you can. It's a relatively easy to learn language. There's a whole bunch of examples, and you can cut and paste something and give it a shot and see. The compilation is a little bit slow right now because we are generating Java bytecodes and we do a bunch of work there. That'll get better over time. There's a release, I think there's a 103 release that went out today. And we're doing bi-weekly releases of patch releases, and there'll be a quarterly minor version release coming out. So December 18th, we are planning to do 1.1 release. And then from there on, we'll have a dist update mechanism. You don't have to download again. You can just say update itself, and it'll update itself from that release onwards. Right? Or it'll self-update if you let it do it.